maybe edit before send to YouTube. Okay. Okay. So I think for those of you, for those staff have been here for more than half a year, you may have heard about this. Okay, last time downstairs in the conference room, because actually this slide is from last time when I gave this internal training. Okay, but here I think after even you had this a second time, I think after you hands on some modeling work, you may have a deeper understanding. Okay, or you may have an opportunity to ask more questions. Okay, so that's why I think it's good to go through this again. I think before that, let's welcome our new staff training. Yeah, you want to have a self-introduction? It's okay. Okay, so yeah, actually training is a very senior software developer. And used to be the CTO of some startup company. Okay, also in our domain, of the maritime and logistics. So, so in future, if I have any questions about development, coding, programming, can approach him. Okay. Okay. So as you may know, that our work here actually have this two layer. Okay. So when we want to build a simulation model for some industrial systems, actually there's two phases. One phase we call the modeling. Okay, modeling meaning that when you see a systems, okay, you see a system actually in a different way from the normal industry people look at it, okay? Because your purpose is to build a model for it, okay? So you need to understand some of the key points, the structure, the components of the system, and how each of the subsystem interacts. So this is some things you need to understand. And this process we call the modeling, okay, to conceptualize the systems. Then the second one will be the development. Okay, development is more like how to interpret, how to describe this model, the conceptual model in your mind, in a computer language. Okay, so this is actually the second layer. Okay, so I think if you are a good programmer, so probably you are very good at the second phase, like what Lisa is good at, and also training your expertise. Okay, but for the first phase, how to understand the industrial systems. Yeah, so this is some things I want to introduce to you in this few days. Okay, so this is the purpose. So yeah, so let's start with this one, the systems and the computer simulations. I think the first questions you may ask yourself whenever you look at one system is to ask, what is actually a system? Okay, we're going to model. So here are the three questions you need to ask yourself. The first one is, for system, every system is actually have a purpose, okay? So when you look at the system, you need to ask, what is the purpose of these systems? I think some of you have already started to build some simulation model or module, okay? So you may take this as one of the example to ask this kind of question. For example, like Ye Hong is working on the yacht set, right? So yacht set, what are the purpose? The purpose is to get a container from the vehicle and step, okay, onto the block, the yacht block. Or maybe unstep some container from the yacht block and mount to the vehicles. Okay, so this is the purpose of the yacht set. Then I think take another example, like Monica is now working on the modules for vessel generation. Okay, so the purpose of this module is actually generate vessel and together with all the demand on these vessels for importing container, exporting container, and the transshipment of the containers. Okay, so this is the purpose of this module. We have another example like the key cranes. Okay, the key crane is actually get a container from the vehicle and put load or discharge from a vessel. Yeah, so these are all the some of these, and also the same as for the traffic. Okay, so this is the first question: is what is the purpose of the system? The second one will be that what are those components of this system in order to fulfill this purpose? So what are those things? Okay, inside this system, you need to use or you need to interact, plan, coordinate in order to achieve these things. Okay, so for example, same example like yacht set, we have the yacht crane, we have the block, we have vehicles, okay, and we have the docking base, okay, the position where the vehicle can stop. And for the key crane, the same things, vehicle, the key crane equipment, and also the vessel, the bay, the storage. And for the generator, okay, then actually we have a vessel schedule. We have each of the vessels. Yeah, we have a realization of the vessel arrivals, including also those logical entities. Okay, So those are the, I should say, the components of the system. This is the second question you need to ask. Okay. Then after this, the third one, the more important thing is how those components actually work together, interact together, okay, to fulfill this purpose. I think this is the first three questions you need to ask whenever you want to model some things. Okay. So yeah. So this is the first part. I mean, if this course is given to some student, probably this is some of the exercise I want the student to go through. Right now, I think there's no need. Okay, maybe after work, if I'm interested, you can play with this exercise. Okay, to look at the different system and try to explain what are the purpose, what are the elements, components, and how they interact.
Maybe you can explain anyone.
Okay, yeah. So anyone want to choose an exciting example?
I think. Yeah, English.
Okay.
Maybe D.
Yeah. Okay. Warehouse is more useful. Okay. So who want to try? What's the purpose of D?
Logistic.
You want to try?
Logistic, right?
It's a warehouse. It's a warehouse.
Logistics.
Yes. Purpose is for logistic.
Yeah.
Okay.
And more detail.
More detail.
Yeah.
A story. So story, but on this.
To receive items, storage, and then
Keep a storage.
keep a storage, and then
Warehouse.
packing them back.
Customer demand.
Warehouse.
These are customer demand.
Meeting the
As a
customer
buffer?
demand. Yeah.
Yes.
Buffer, yeah.
It can be a buffer.
Yeah.
Transit.
Transit, yeah.
Okay. So actually, I think we are doing some of the warehouse project, and you can see that for each of the warehouse, the detail purpose can be different. For example, sets. Okay, it's more for transshipment. Okay, from airplane to airplane, aircraft to aircraft.
Yeah.
Then for like micro, it's more for the manufacturing. They actually order some like the components. Then they need to serve as a buffer so that when you start to manufacture, produce, you can actually get those components from the buffer.
Yeah.
Okay, to make sure all the processes are in time. And we also have like a co-analog, so probably it's for distribution purpose. Yeah, actually you see that even it's for, I mean the general purpose is for logistics, for storage, but in detail the purpose can be slightly different.
Unique.
Okay, so yeah, then also because of that, then the way we design the system will also be different. Okay.
Yeah. Yeah, for some cases, once the item move into the share, then we can kind of some how we kind of interchangeable. For example, I know here and for rest here, I can create a sum. But for those kind of access the case adjustment, this one is uniquely to go to there so that one cannot be mixed and other stuff.
Yes. So we need to consider the purpose. And also for the components, you can tell what are the components of the D. Some high level components.
Right. Boxes. The right.
Box is a SKU.
SKU.
Some parallel.
Yeah. What is it? The rack. The rack. Yes.
Transporter.
Transporter. Yes.
Transporter very general can be some different type.
The traffic.
Yeah. The traffic. Transporter.
How do they travel? Yeah. Do they really have any kind of the travel rules? So this one only to move from another direction or anything can be put in due direction. These are some different.
Yeah. So any ideas from this team who are working on the warehouse model?
Like resources will be there.
Resource? What kind of resource?
Like one is a manual resource worker. Then we can also have the transporter.
Have labor, vehicle,
Yeah.
material handling,
Material handling,
storage, packing machines, space, human labor. Yes, these are our things.
So let's consider
Inbound down,
components.
down.
Yeah, that's our components.
Okay.
But basically, I mean, later we can have a systematic view for this one. For example, if you compare with what we did for the ports, for the container ports, so what we can see is they actually have a docking area, okay, docking space, okay, for vehicle. Then we have the processing, like a staging area for inbound and staging area for outbound. Okay. Then we have transportation systems or material handling systems. So it can be a transporter, can be human, can be like forklift, or we consider as a transportation system.
Conveyor.
Yeah, conveyor. We have a different kind of transportation. Then we have a storage. we have a rack, we have like lot of other things. Yesterday we mentioned about different
VML.
we have BLM, we have different kind of storage systems. And sometimes you can see the storage system kind of integrated with a transporter. Like VLM, they have a lift built inside, and we have the IS, what's it, shuttle, multi-shuttle kind of things. Yeah, they also have like vehicles built inside the storage systems. So these are some things we also need to have in mind. Okay, so yeah, so this is about the P, and then the next question is how they will work together. Yeah, how they work together. So basically, you can think about the process. Okay, for example, the P, you can think that the inbound process. They have an inbound process, which a cargo will go through certain stage, all the way go to the storage. Then it will stay at the storage. And then, like in the outbound process, it will come out from the storage and go through different stage, all the way goes to a staging area, and eventually go to a dock and be loaded to the vehicles. Okay, so these are how we interact from those components. Okay, so this is for D. Okay, I think for the time, from the linear time we just we end it here, then we go to the next slides. So these are some things. I think I also just now I mentioned is about the hierarchy. Okay, so system, it can be so-called atomic, meaning that when you look at system, you understand the component, understand their interactions. But also for some of the systems, the structures can be complex. So in that case, you do not see all the components at one site. Okay, so what you will do is you're trying to divide them into the smaller systems, the subsystems, and for each subsystem you do the same thing until for one of the subsystems you are able to see all of them. Okay, for example, just now for the warehouse, we said about transportation. But transportation can be many things. It can be a labor, driver, can be the equipment, vehicles, also can be different kind of the transportation system integrated together. Yeah, and also for the storage system the same. So so this is why we need a certain time. We need these hierarchical structures to understand the system. Then this system boundary will be very important. Okay, when you build something, you need to define the boundary. Okay, then you only consider those things inside the boundary, but ignore those things outside. Okay, so so here actually, this is actually from the textbook. To see that for one of the systems, you need to consider what are the source system, what are the wider system, what are the target systems. I think if you link to what we are doing here with all this modularized modeling, okay, I think the way you need to think is what is the boundary of the current system you are building, current module you are building, and in what kind of circumstance this module can be applied. Okay, so what are the application scenarios? And the other thing is, in order to build this module, so what are the sub-modules you need to use? Okay, internal, inside. So actually you have a current module, you have a smaller one, which you grab and put in. Okay, then you also have a larger consideration to see how this module will be used. I think that these are some of the concepts you need to bear in mind. And here actually I gave one of the example of how we build. They use this hierarchical structure to build a model for the container port. Okay, so we have these 5 levels. I think I already talked about this many times. So so I won't repeat, but later probably training or maybe some new stuff. You still have a question later, I can explain to you. Okay. Then one of the very important things for to understand a system is actually this so-called state variable. Okay. Why we say this is very important is this actually is our view, describe our view, how we understand, how we perceive, systems. Okay, because the system can be the same. It can be the same system, but we can use a different way to understand it. Okay, understand this system. I just take this example. Okay, so now if you think, now this is the system, so I am the only components inside. Okay, like teaching a course, or maybe I just moving inside this classroom. Okay, so if I want you to describe the state of the system, or maybe more precisely the state of me, okay, how do you want to describe me, my state? If I keep working, you may see that the position of me will be one of the state variables. So in that case, every second, every millisecond I'm moving. So you need to keep updating the coordinates of myself. Okay, so this is the one way to perceive my state, okay, in this system. Or maybe you can see that, okay, now you do not really care about the exact positions of me. You just want to see that whether I'm in front of this TV. Okay, so in that case, now I'm not in front of TV, but while I'm working here, after some times, I start to stand in front of the TV. So actually you change my state from a false to true. Okay, then later if I walk away, then you change my state from a true to false again. Okay, so you can see that for the same systems, you can actually use the different state variables to describe the system. And this really depends on how you want to describe it, how you want to use your model to help you to solve your problems. Okay, so these are some things you need to bear in mind. So,
can I ask, for example, is the state is a derivative of an action, or snapshot of an action?
It's a snapshot
of an action. Walking is an action, right?
I think it has nothing to do with action.
Nothing to do with
Nothing to do with action. Even you initialize a system, then apply no actions to these systems.
Then
you still have a state. You still have a state.
State is doing nothing. Right?
Yeah, it's doing nothing. The state will be keep the state will be constant. Okay, it will be a constant. Yeah. So state itself has nothing to do with action events. State is just a snapshot of the systems. Yeah.
Okay.
Yeah. Okay. Okay. So actually depends on how you want to describe the systems. We actually divide the state variables or the system descriptions into these three categories. Okay. One is that if the state variables is discrete, okay, or maybe the change of the state variables is actually according to certain discrete event. For example, as I just mentioned, before sometimes I'm off, or after some time I'm on, or false and true. Okay, then you see that this changing of the state variables is actually discrete based on certain discrete event. So in that case, we call this system as a discrete event systems. It's not because a system is a discrete event, it's just we use a discrete event system to describe it. Okay, so this is something we need to understand. And the second one is if you see the system as continuous. Okay, as I just said, and keep changing my coordinates, positions. Then in that case, you actually model a system as a continuous systems. Okay. Then the third one, I think you can kindly just ignore. Okay, the quantum systems. So if you want to look into a very small system, very large systems, then probably you need to consider as this one. You have maybe multiple states at the same times. Okay, have a superposition. Yeah. So this one, if you have interest, you can discuss later. Okay. So then the next question is, how do we want to? What is the best ways? Okay, we should apply the different perspectives to describe the system. What time we should understand it as a discrete event system, what time we should understand as a continuous systems, or even what time we should understand the quantum systems. Okay, so this actually gives you a guideline. Okay, so if you look at every system in the universe, okay, from a very small one to a very large one, okay, the small one is as small as a subatomic, okay, world. Okay, the large one is as a cosmological systems. Okay, you can see that at the both ends, people describe it using as a quantum systems. Okay. Then if you look at the slightly small one, but something we can touch, okay, we can feel, we can see that people usually look at it as a continuous systems. When people mention about like material flows, or maybe some physical or chemical properties. Okay, if you think that to this kind of the things is of your interest, okay, then you actually model it as a continuous systems. Okay, I think one of the good example is the car. Okay, is a car. If you want to simulate a single car, how a single car moves, or how a single car will behave when you do some operation, when you drive this single car. So how do you model it? You model it as electromechanical systems. Okay, means you move your steering wheel, okay, then you will trigger some mechanical change, then this will change the behavior of the vehicle. If you press on the accelerator, then there's something change internally, then the car start to accelerate, or if you press a brake, then you will stop. Yeah, something like that. You can see that all those properties, the behaviors of vehicles, it should be described continuously, okay? Continuously. So this is about the electromechanical system.
Like Newton's third law.
Sorry?
Like Newton's third law.
Yeah. I mean, if you look at, as I just mentioned, if you want to look at the physical properties, chemical properties, these are some things you need to consider. Yeah, you need to model as a continuous system. Well, another examples I think in our studies is about last time the AGV transponders. Okay, you still remember that example? Is we're actually simulating the movement of AGV and how it's touch and sense the transponders planted on the ground. Okay, so in that simulation, it's actually a continuous system. It just later we discretize it into a discrete time simulation. It's not really a discrete event simulation, a discrete time simulation. We are applying some approximation techniques, okay, to do this. But because it's a discrete time simulation, so we actually build some like a dummy events, okay, to use a discrete event simulation to build a discrete time simulation to approximate a continuous simulation. So this is actually the principles behind. Okay, behave by nature is actually a continuous simulation. This is something we should need to know. Okay, then the second thing is when the number of the vehicles increases, okay, into a certain level that you are not interested into the individual behavior, the behavior of an individual vehicle. You do not care about how the drive turn the wheel, the steering wheel. You do not care about how it press the accelerator or brake, but you care about the positions of the vehicle or the mission, the job the vehicle is doing. For example, you are managing a fleet of the taxi, okay, vehicles, okay, or maybe you are now deploying in charge of a fleet of AGVs, for example. Then in that case, okay, you are making some of the decisions based on the state change of the whole system. For example, when the job finished, you need to assign another job to it. When there's vehicles become idle, then you need to consider to deploy or when the chair is idle, then you will consider yeah. So these are all the you see that all those decisions, you care about those decisions, and the decision is not made continuously, but only when certain things happen, it triggers you to think about to make another decision. So in that case, you can see that we actually model it as a discrete event system. Why? Is because the decision occurs as a discrete event. So that's a reason. Okay, so you see that when the system becomes larger, okay, then actually our focus is from a continuous system to a discrete event systems. But what happens if the number of the vehicles keep increasing to a level that we do not really care about those decisions? Let me give you an example. If you want to model the traffic in the whole Singapore, the urban area, do you care about each taxi company, how they make a decision? Do you care about each individual, how they want to go to a car park to start his car and drive home? You do not consider those things, but rather you actually consider the whole demand as a flow. Okay, it's like at a certain time the flow starts to increase, and up to a certain peak time, then they start to decrease. Okay, so if you do not really care about the behaviors of the individual components in the group, okay, then the system becomes a so-called socio-economic or ecological systems. Okay, so in that case, we use a continuous system to describe it again. Okay, so another example will be like when you look into the economics. Okay, you look into the supply-demand curve. So this thing is a continuous. Okay, you can see that the demand can be 1.2, can be 1.25, can be 1.253. Okay, but actually we are not talking about individual like a computer, 1.25 computer. This is not what we mean. But actually we are looking at a very large scale. We do not really care about individual customer, individual product, but we are looking at the trend. Okay, or in other words, you can think like this. Okay, so if we are looking at some systems purposely managed by human decision maker, usually it is this one, industrial system or discrete event systems. Okay, because human man-made system is usually controlled by discrete event decisions. Okay, maybe another example will be computer designed by human. So everything inside is actually discretized. For example, like the CPU cycle. Okay, every cycle is how many? 1 million,
Yes.
30 million cycles, but it's still discrete event. Although it's a many event happen, but it's still discrete event. And also like for the monitor, every second 30 frames. Okay, so this is also discrete event. It's a discrete. But if you look into this one, for example, like electricity, okay, or making material, or the air, the liquid flow, so those things are not designed or made by human. Okay, or in other words, it's made by creator, God. Okay, so in that case, it's continuous. How about this one? You say this is also related to human. Okay, but this is related to human society, but it cannot be controlled by human. Okay, if it to the secret levels, then you do not really control or design by the human, but rather you need to follow the rules. Okay, in this society, and those rules are something existing there. Okay, so in that case, it's not controlled by memory systems. So in that case, we'll use a computer system again.
Yeah, okay. That one is considered as a kind of open system.
Yeah, open a large. Yeah.
Initially, it's considered as a closed system. Closed means everything is controlled.
Yeah, everything is controlled. Okay. Then for these two, just the thing that's supernatural. Then we just ignore.
So for the 1, 2, 3, 4, the fourth one, for example, like climate change, so it's become the continuous system because
of course.
we cannot.
Yeah,
So it's like a collection of a small discrete systems.
Yes.
And how about fly by wire? For example, like airplane fly by wire when we actually do electronics, and then there is another so-called a pump to push the it's electronic. Is that considered discrete or
chemicals based on what kind of problem? If you want to like test or experiments on the mechanical design, the hardware. I mean, if you want to do those things, they become more continuous. But if you want to test that, you can also do it at a high level to see that how the pilot responds to certain circumstances. Then it can be discrete. Meaning that you just risk a certain event, then you test how the pilot responds to it. Then you can use a discrete event system. Okay. Yeah. So in that case, we will be very clear to say that now if we want to model the warehouse, if we want to model the port, container port, what kind of system we should use. So definitely it should be this one. Okay? Yeah, so this will be very clear. Then we go to the next one. Is okay, what is a simulation? I think you should know what is a simulation, but how to classify a simulation, what type of simulation. Just now it's actually from a state point of view, okay, to classify, actually it's not simulation but systems into continuous system, discrete event system, and quantum system. But here is about the simulation. Okay, so what kind of the simulation we can classify them? So here actually we have these two major types. Okay, the first one we call is an analytic simulation. The second one we call the virtual environment simulation. So let me just try to explain what does this mean using this graph. We have a computer simulation. The first time we call the analytic simulation, and we have this bracket. This is very important. If you understand what is written here, I think you know the difference. Yeah. This one is called a timestamp simulation, meaning that everything happens inside. Everything happens inside. We just need a timestamp. Okay, we just need a timestamp. For example, like just now use the case. Okay, I start to step in. Okay, so if you want to describe the change of state, you just give a timestamp to it to say that at a certain hour, which minute, which second, Hopin comes in and start to stand in front of the TV. Okay, so this is the ways you need to do it. But when you say this, okay, or maybe after maybe 5 seconds, okay, I step out, okay, then you say that, okay, at which hour, which minutes, which seconds, okay, Hopin step out. Okay, so this is some things you need to describe while you are running, practice your simulation. But the thing is, do you really pause here for 5 seconds before you say the next sentence? After you describe how being step in at which seconds, do you need to pause yourself for 5 seconds before you say the next sentence? No, right? You can just say immediately after the first one, and every second hopping comes in, every second the hopping comes out. Okay, so these are the ways you are describing or practice running your simulation. So in that case, we call this a time step simulation. Okay, but in the other ways will be different. We call it time delay simulation. You do not really need to describe or tell the other people that which hour, which minute, which second. Okay, but just need to say hopping comes in, then pause there for another 5 minutes or 5 seconds. Then you say hopping comes out. Okay, so this is the ways you run your simulation. Okay, so you can see the difference between these two. Okay, then you can see that what are the purpose of these two different kind of simulation. The first is actually for analytical purpose, right? Because for analytics, we do not really need to feel the delay, but we need to quantitative description of what is happening here. So we need everything to be time stamped. Okay, but for the next one, we call the virtual environment. This is more like for the training of the people. So we need to give the people a similar or exactly the same feeling as the real world. So that's why we cannot tell a person that this is the time. This does not work. But we need to give the person a feeling that this is the time past. Okay, when some event happens. Okay, so this is about the virtual environment simulation.
So that one is considered to do for the animation.
Yeah, when we do the animation, actually we need to follow this one because we need to give people a feeling. But when we do analytics, answer some questions, optimization, we just need to go to this one. Okay, so this
one is the event and this one is the time.
Yeah.
No. There's nothing here. I'm not talking about the event because here it can also be event.
But different meaning.
It's just a driven purpose. What are or maybe I should say that what are the outputs the simulation need to achieve. So this one need to output the timestamp, okay? But this one need to output the experience of the time.
Then my question is, when you do the timestamp simulation,
yes.
The time when it starts and it stops, or only when it starts and don't care about the stop?
Every time, everything happens.
Okay, so we stamp, state change, stamp again.
Yeah. Everything change. Every time the state change, then need to be timestamp. Yeah, timestamp. Okay. Then this timestamp can happen is very fast. According to
for example, in the kind of case, maybe here the timestamp is talk about the first hour, and then the next event is 8 hours. So the clock will trip to the 8 hours with the other 8 hours. There are numbers of the event. So that the clock may jump very slowly. It depends.
Yeah, for this one, then you need to wait for 8 hours or proportional.
That one is a real time, right? It's like real time.
Real time or real time scale, according to a certain time scale. Okay, so or maybe you can take some example. I don't know whether you play a computer game, okay, like Age of Empire or those things. Okay, for example, Age of Empire will become like this one because it has really virtual experience.
Oh yeah.
Okay? But actually for the JP project. Yeah. And for this analytic simulation, so you can think about another kind of simulation will be like let me see what are the this actually I know many Chinese computer games like cyber so what I'm saying it's like it's a periodic operation. Oh, you know the civilization? You know the civilization?
Yeah.
Okay. Civilization is actually you take turns to make decisions. Okay, like or maybe the chess. When you play a chess, it's actually this analytic, it's a timestamp. Okay, because you don't really care about between the two moves, whether it's a 1 minute, 2 minutes, 3 minutes, you don't care. It's all the same.
Yeah, it's like when we play chess, we stamp and then we move.
Right.
We stamp, we move, we stamp.
Yes.
Maybe some of them like 三国志.
Yeah, 三国志 is more like this.
But when you compare between two teams, go to virtual VE. When you see after two
no,
teams.
it depends on how you design the game. Because if the second one is more like chess, you take turns. You take turns. Take turns should be this one. Yeah, but this is more like
real time to fight between two teams.
For example, the Age of Empire. Okay, if you make certain actions fast or slow, it actually make a difference to the game result. Okay, but for the chess, actually it's not sensitive to that. Only when you exceed the time limit, then it's a penalty. Okay, so this is
immediately soccer must be on the right.
Yeah, soccer is on the right. Okay, so this is the first classification. Okay, okay, to divide this into this two category. Another thing is,
So manager.
if you want to look inside each type of simulation, then the next question is whether there's any interference from the outside. Whether it's an autonomous computer simulation or it has some interference from the external party. What are the external party? It can be a human, can be operator, can be a software, can be a hardware. Okay, so let's take this example.
Yeah.
If there's no interference from outside for analytic simulation, this one we call it autonomous analytic simulation. So these are actually the most of the simulation we're running here. Okay, we start the simulation, we wait until the end, okay, then we read the result. Okay, so this is about the autonomous analytical simulation. This is the most common in this room, I think. Okay, the second one will be the constructive simulation, meaning that the simulation run for some time, then you pause. You wait for the human in loop. Okay, wait for the human to make a decision for this simulation to continue. Okay, so this will become so-called a constructive simulation. So this will be like a civilization, as I just mentioned. Okay, it's actually a human in loop simulation, right? Every time, okay, wait for you to make one decisions before it's a continue and let the other players make the decision. So this is about that kind of a game. And I think this is okay. And also, if you want to apply this concept to the industry, we can see that this might not only be a human in loop, can also be a machine in loop, software in loop, hardware in loop. Yeah. Okay, so if it's that case, then it becomes another thing we refer as emulation. Okay, so what does this emulation mean? Let's give you one of the example. If now a PSA design a new TOS systems, terminal operation systems, okay, they want to test whether this TOS system work or not. But now they cannot deploy this TOS system directly in a pod because the pod is actually operating. Okay, if there's any problem, then they make some trouble to it. Okay, so what they can do is they build a simulation, but they let this simulation to receive instructions from the real TOS, from the real software. Okay, so what will happen is when this software gives instruction, then the simulation move until a certain time point. The simulation will actually pause there, waiting for another instruction or maybe feedback to these software systems. Okay, waiting for another instruction to come in to continue the simulation. So in that case, this kind of the simulation we call it emulation, and this is quite common, meaning that in our team, besides doing these things, this will be another things our team might need to focus. Okay, in the future. Yeah. Okay, so this is about the analytic simulation. Then here we also got the virtual environment simulation and the same similar things. If there's no interference, okay, from outside, then it becomes a so-called virtual things, virtual simulation. Or maybe I'll give you a better name to understand is just an animation or it's a movie. Yeah, because they give people some demo without any interference there, then it becomes a movie. Okay. Yeah. Then the second one will be constructive. And I just mentioned that consider the virtual environments with a human involved. Then what is looks like? Again, okay? Or maybe like some training, like you're driving a car, driving an airplane, or maybe I think the last time, is Herman here?
No, not here.
Okay, I think Herman last time mentioned to me that they are actually designing, last job is actually designing certain software to train certain personnel. The battlefield or whatever. Okay. Oh. Yeah. So.
Oh, okay.
Oh, you also have experience like that.
Yeah, because we are working on the
you
same
also
project.
Yeah.
So previously
with Herman?
Sorry.
With Herman?
No.
Or maybe I remember wrongly.
Yeah, with Herman. I mean, like I'm continuing his job last time.
Yeah. So this is actually more like this one, constructive virtual environment simulation. Okay. And also I think the SP, Singapore Poly. They have this COE working on the vessel, the marine traffic simulation for the safety of the vessels. So their simulation is actually this kind. Okay, so this is the things we need to be clear. And also we have this one, which the simulation actually have human in loop and also machine in loop. Okay, so I have both interference from the human and machine. Then this one is more like a monitoring or surveillance systems or a control tower. Okay, it's everything is driven by outside. Okay, then you need to human to make a decisions. But the simulation itself, software is actually just a monitoring systems. Okay, then it becomes this live system. Okay, so yeah, so this is the type of the simulation. The purpose of this graph is like the next time when you want to understand, when you heard about some people saying that they are doing the simulation, then check clearly what kind of simulation they are doing. Okay, using this one, or probably the slides before, the previous slides. Okay, to see that whether there's a continuous simulation, whether it's an electromechanical system or it's an ecosystem, okay, or it's just a discrete event systems. And also come to this page to see that whether it's analytic, virtual environment, or whether there's any interference from the human or hardware or software.
So like CCTV camera will be which simulation, the third one?
I think it should be this one, but it depends whether people will call it as a simulation. Okay. Okay, whether people call it simulation. I said it's a kind of simulation because what you see from the screen is not real. Like actually some image and you replicate here. And this replication and the pace, okay, you move this replication is actually depends on all the sensors or cameras. Okay, so in this sense, we call it as a simulation. But usually people do not see this as a simulation. But just imagine that what you see from the screen, okay, is not the real image, but rather something like a 3D model. But you make this a 3D model move at the same speed as the real systems. Then this become people may call this as a simulation. But this simulation by nature is the same as the last one.
Emulator.
No, in emulator we more
Emulator.
refer to this one. Emulator.
Oh, emulator. Oh, okay.
Emulator is actually for analytical purpose.
Yeah.
But this one is actually for human. Or maybe we should say that analytics is more towards the machine algorithm. But this one is more towards people human. If a human is not there, then I think it's not necessary to do a time delay simulation. So emulator is for analytical purpose. So that's what we should categorize into this set.
The human the delay is to let human in order to make the real-time experience and also to do the more precise image.
Right. And also, one more important thing is here if you want to repeat the second time, most of cases you have the same result. If you control your random stream, random series very well. But for this one, if you repeat the second time very hard, you will get the same result. If you play the same game 2 times, Star Wars, Age of Empires, you will totally goes with a different result. Because it's a human involved, because it's a time delay, okay, which are not precisely controlled. Okay, so why simulate? I list some of the questions. I think for you is because you want to maintain your job here, so you need to do the simulation. Okay, so then the second one, then now we talk about the type of the simulation. This is more like methodologies. So just now I talked about how to classify the simulation is from like a principle or theories, but here is more like methodologies. If you want to do a continuous simulation, so what kind of method you should use? And if you want to do a discrete system, so what are the methods you should use? And also, is there any other method, okay, which are about the simulation? Okay, and here I give this 3 of the examples. The first one is for continuous simulation. We're using this so-called system dynamics. Okay, system dynamics. So meaning that we are describing the systems. We are describing the systems by variables. Okay, the first is variables. Each of the components and properties by variables. Then we actually describe the relationship. Okay, the interactions between the variables by using the differential equations. Okay, differential equations. Why differential equations? Because the time plays a role inside. Okay, you can do some like integral. You can do a differentiation. Okay, so this is about the system dynamics. Okay, then for example, like here we consider when you do a banking, you consider the principals, interest. Then see that while time going on, then the interest is actually is related to the principles. Then the big principle will become an integral of the interest, etc. Okay, so actually you are describing these relationships. Then you run the simulation, you will be able to get a result to say, okay, so after 1 year, so what are the principles, okay, or what are the interests at that time. Then you can use the different, we call it, I couldn't remember the name. Okay. But I think many of the methodologies you can refer to this book if you're interested. Okay. Then the second one will be, this is important for us, which is actually discrete-event simulation. So how to do a discrete-event simulation, I think later I will try to explain to you. Okay. Just remember, this is how we describe a discrete-event systems. Okay. Then also, like for the discrete-event simulation, there's a several modeling approach. Okay. So later, I will elaborate to you that what are these three mainstream of the modeling paradigm methodologies. And now we are using ODS, so what are the relationship of the ODS regarding these three streams? Okay, so later I will talk to you. Then there's another kind of simulation we might not use frequently in our group, but it's actually very popular in other like scientific studies, while the time is not an issue. Okay, which one we call the Monte Carlo simulation. Okay, Monte Carlo simulation. Just remember one point is time is not an issue. There's no time dimensions in Monte Carlo simulations. Okay, or maybe you can see that this as a projection, or maybe you can see that discrete event simulation or continuous simulation is actually an extension of the Monte Carlo simulation on the time horizon. Okay, it's like when you have a 2D printing, and you extend to 3D. Okay, so it's like Monte Carlo is a simple form, and you want to extend on the time dimensions. You actually decide on the two-way. One is that you extend continuously, then become a continuous simulation. If you want to extend in a discrete event or discrete time, then become a discrete time simulation. If it's based on discrete events, then become a discrete event simulation. So these are the things. So now let's look at the Monte Carlo. One of the example, okay, is that how we calculate the areas of this circle. So of course you can use a radius and use pi, okay, to calculate. But we can also use a Monte Carlo simulation. Okay, how to do it? You sample one point in this square. You know how to sample uniformly? You choose one uniformly from 0 to 2 for x, another 0 to 2 for y. Okay, then you sample one point from this square uniformly. Okay, then the second things you do is you check whether this point is within the circle. By doing what? By measuring the distance from this sample point to the center of this circle, 1, 1. Okay? By using the formula. What's the name of formula? Chinese is a good wording, but I don't know.
Coordinate.
Sorry?
Coordinate distance?
Like
Euclidean distance.
Euclidean distance. Yeah, just Euclidean distance. What is the formula? The name of this? Yeah, but I know. It's fine. I think all of you know it. So, by the way, the pi is not involved. We just need to calculate the Euclidean distance. Okay. Then we can see that whether this distance is within one, smaller than 1, or larger than 1. Okay. If it's smaller one, we mark it as 1. If it's a larger than 1, we mark it as 0. Okay. Then we do this sampling and the calculation many times. We calculate what are the probabilities to get 1. Okay. Then we time this probability by the area of this square. We'll get the area of the circle. Okay.
No time. Yeah.
No time. Okay. Because the first point is not earlier than the second point.
Yeah.
Right. And also when you sample 1,000 points, does not mean this means have a longer time than the 10 or maybe tens of thousands.
So then the data can be in computational field that can be doing as a kind of modification.
Sorry.
Kind of like using the modification approach in order to.
So it's just time is not an issue here. Then the same things happens for this one. Okay. When you want to calculate the area here, I think I will leave this to you consider how to do it. This is the same thing. Okay. So this is called a Monte Carlo simulation. The time is not involved. Okay. Then I think I think this part I will skip. Then I will jump to the second slide. Second slide will talk about the discrete event simulation. Since the time is
Yeah, I think
up,
tomorrow can
maybe add it before sending it. Okay, so I think for those people, for those staff have been here for more than half a year, you may have heard about this last time downstairs in the conference room, because actually this slide is from last time when I gave this internal training. Okay, but here I think after even you had this a second time, I think after you hands-on some modeling work, you may have a deeper understanding. Okay, or you may have an opportunity to ask more questions. Okay, so that's why I think it's good to go through this again. I think before that, let's welcome our new staff training. Yeah, you want to have a self-introduction?